try to do completing the square. It's going to be a long video, so feel free to fast forward, especially the concepts you already get. But I would strongly suggest either click on the link below that jumps to partially completing the square, or jump to about 3/4 of the way through, because I actually find partially completing the square a much better system. Okay, so here's our goal. Our goal is we're trying to reach a vertex format for a quadratic parabola. Okay, sorry about the spelling there. So we're trying to get from this to that. And we're using perfect squares to get there. So I'm going to read that again. Our goal is to reach the vertex format from this format, so the standard format, which is sort of written out over here. Okay, but we're trying to do it by manipulating our standard format into the vertex form using perfect squares. So we need to understand perfect squares. Here are some examples of perfect squares. So I've written the expanded form here just so you can understand that this is the same as that. And that when we expand a perfect square, we get this pattern, x squared. So it looks like this first unit is squared. And if we jump right down to the 9, it looks like the last unit is squared as well. And then we get this thing here. And it doesn't take long to realize there's a pattern in the middle as well. Let's go to this next one. Yeah, there's the x squared is minus 5 squared. Yep, we get plus 25 because minus 5 squared is plus. And then we get this thing in the middle. So really we need to understand, and again the pattern repeats itself here. And then we need to essentially, once we see, okay, x squared, and there's the 6 squared in the last one, we really need to figure out what's going on only in the middle. How does this middle get created? And we notice a pattern. The middle is always 2 times the first term, which we're always using, by the way, please note, we're always using perfect squares that do not have a coefficient in front of the x squared. That's important to note. So we're always keeping it smooth to make this process easier, and that means we never have a number in front of the x. And the harder perfect squares, we have to get rid of that number if there's a number, and we'll get to that. So we'll notice in the middle pattern it's always 2 times the first term times the second term. So here's the second term, here's the first term, and it's 2 times it, which of course is 6x. What about this one? Okay, 2 times the x times minus 5 should be minus 10x. Yep. 2 times the x times the 6 should be 12 plus 12x. Yep. So right away we can see that this middle term is always 2 times the first term and the second term. Great. That's when this is summarized. Even when it's minus, all that happens is a minus happens in the middle. But the first and last terms are both plus, and that's because when you square something, they become plus. So even this minus b becomes a plus b squared. If you don't understand it, just take minus a minus b, and times it itself and expand it, and you will always get this. So now that we know this standard formula, we can realize, okay, this middle term, I can figure out a perfect square. Instead of multiplying by 2, if I'm starting with this, I can just divide by 2. Let's look at this theory. Can I guess, without pretending I don't know these, can I guess what these terms are by looking at either the middle or the last? Okay, well, what if I divide this 6 by 2? I get 3. And what's the square root of 9? 3. Therefore, and what's the square root of x? Squared, x. Therefore, I can pretty much guess that this perfect square is x plus 3. Let's see if it'll follow the pattern. If I can divide the middle term and square root the second term and get the same result, if I can divide the middle term by 2, just the number, and square root the second term, will I get the same result? Okay, I divide this by 2, I get minus 5. And what's the square root of 25? It's either plus 5 or minus 5. So which one matches? Minus 5. I can pretty quickly deduce that the perfect square, this is x minus 5, simply because of this minus here. What about this last term? What happens when I take 12 and divide it by 2? I get 6. What happens when I take the square root of this last term? I get 6. And you should always make sure this is square rootable. And since it's always x squared, it always is. And I deduce that, yes, this is probably x plus 6. So that means just knowing this, I can sort of determine if I have a perfect square. And you might say, well, that's great when I have a perfect square. What if I don't? I'm just going to change these numbers a little bit just to give you an idea of where we're going. Pretend for a second it's obvious that this is a perfect square, and this is a perfect square, and this is a perfect square. But pretend for a second that there's another number here, and I'm just going to add another number. 9. Doesn't matter what even if I subtract 6. So it's clear that these become, if I add that number to that last number, I'm going to get x squared plus 6x. Nothing changed there. But I'm going to get plus 13. Like that. And this one, if I add that 9 to the 25, I get x squared minus 10x plus 34 now. And this last one, if I subtract 6, I get x squared plus 12x plus 30. Now it's clear, sorry about there, I got to add the 12x. It's very clear that these last numbers, now that's no longer a perfect square. This doesn't reach that. However, I think you can guess where we're going. If we start with something like this, it's clear that these middle terms it's possible to maybe achieve that, part of it, if we simply adjust this number. And yes, sure enough, if I subtract 4 from it, which makes sense because I added 4, I will reach this part. I will actually reach this aspect. I can convert this. I can convert this to that simply by rewriting it like this and then making a perfect square out of that. So it's interesting then. So if I had started with this, I could simply rewrite it like this, and then I can make a perfect square out of this portion of it, and just remember to leave that extra number around. So that's kind of where we're going. I hope you can wrap your head around that. So even if you can't, I'm going to walk you through it. But again, it's very important you understand a perfect square. Okay, completing the square. And sorry if you see some spelling errors in here. I can see some already. When completing the square, you never want a coefficient in front of the x squared. So first look and say if you have the coefficient. So let's look at a few perfect squares. So I sort of go through this and explain the pattern. It follows this pattern every time, or it follows this pattern every time. Square the first term, multiply 2 by both terms, and square the last term over and over again. Side note, you can also learn any expansion called through binomial expansion. So that's another thing you want to investigate, binomial expansions. This just happens to be binomial expansion of squared. By the way, I forgot the little squared here. Okay, so then I review it again. Please note the connection of this term to the two original. It's 2 times 3 times x. Step 2, once you grasp this, once you get the idea of this connection, you can work backwards from any polynomial. Let's start with this one. Obviously, this is not a perfect square because this beginning part, x plus 3, and how did I come up with that so quickly? X plus 3 squared. Well, I simply divided this term by x, my first term, and by 2, which I knew all these middle terms are multiplied by 2, to get the last term. I know that x plus 3 expands into x squared plus 6x, which is what we want up there, right? But it has this nasty little plus 9, which is not there. I mean, now technically the plus 14 is there. And what some people do is once they spot this part of the perfect square, and they go, okay, I can see the x plus 3 is there, and the x plus 3 is what I'm aiming for, x plus 3 squared, but it expands into x squared plus 6x, which is what I want over there, but it has a plus 9. Some people just then say, and this works for you for the simple ones, okay, this will work for the simple ones, you can just take that plus 14 and you can borrow it. You can just say, okay, well, I'm going to do what you just showed me last page. I'm going to break that 14 up into plus 9 and plus 3, and plus 5, which is what 14 is, 9 plus 5. And right here I have exactly what I need. That's a fair method. You can go ahead and do that with the simple ones. It's quite clear that the thing in the black box is x plus 3 squared, right? We just reviewed that. So that's one method for sure. And what's left over? That plus 5. That's definitely a way to do it for simple ones, but it doesn't always work with the simple ones. So I'm going to walk you through, or it doesn't always work for the harder ones. So I'm going to walk you through a method that will work. You want to focus on this part. So right back here, we're stuck with plus 14. Okay? So you want to focus on this part and just move the plus 14 to the side. You know that this can be achieved, and ask yourself, what perfect square would create just this portion? And you know right away it's x plus 3. We just did it, right? Squared. But it creates what we want right there. But it also creates something that we don't want, this plus 9. So we want this part, but we want to get rid of that 9. Well, I know the middle term is 2 in the first two terms, so all I had to do is take 6x and divide it by 2 to figure out x plus 3. So get used to that. If you're facing with this, all you have to do is divide this number by 2 to come up what the perfect square would be. So x plus 3 is simply this number here divided by 2. Get used to finding that pattern. So I know this will produce this portion that I want, but I also know it will create a portion that I don't want. So I know the middle term is 2, the first two terms, so all I had to do was take 6x and divide by 2 and by x, technically. I get 3x. Since the first term is x, I know that the second term must be 3. Note, this is why having no coefficient in front of the x squared is important. Yeah, it doesn't work if we have a coefficient in front of the x squared. If back here we started with a 6x squared plus 6x, we'd have to do something about that 6, but that's the next page, okay? We're working with the simple ones first. You have to walk before you can run. The problem is, when I expand x plus 3 squared, it also produces an unwanted 9. Okay, so next step. All I do, if I take x plus 3 squared, I end up with x squared, and I'll put in green what I want. I want the x squared plus 6x, but I end up with this unwanted plus 9. All I have to do is subtract a 9, right? If I want x squared plus 6 out of my expansion, but I end up with x squared plus 9, all I have to do is take that, which creates this, right? And then subtract the unwanted number that I don't want. That's all I have to do. Figure out what my unwanted number is and then just subtract it. All right, fair enough. This means that if I want x plus 3 squared to produce this part of it, I need to get rid of that unwanted 9 by subtracting a 9. That's all I'm doing here. That's all I'm doing here. Since I know this part expands to this part, I then simply subtract a 9 so that I get what I want and get rid of what I don't. So then I expand it. When I expand this, it's clear. Look at that. So I'm going to expand this. I get that. I subtract the 9, and I get what I want, exactly what I want. Then, now that we have this part of the formula established, we bring back in the plus 14. Now, what's minus 9 plus 14? It's clearly plus 5. And you might say, well, that simple method you showed 2 seconds ago is a lot easier. And yeah, you're right. So is completing this, partially completing the square. That's why you should get to that, because that's even simpler. I can now bring back the 14 and add the like terms. So my completion of the square for this is actually that. And yes, I could have simply broken it down like this. X squared plus 6x plus 9 plus 5. I could have just borrowed the 9 from the 14. That works fine for simple ones. Yes, I could have just taken this 14 and broken it down into the 9 I want and the 5 I want. And I would be left with the same thing. As I said, that works fine for simple ones. Let's go back. If I want to make sure I've achieved my goal, I simply expand this. So I get this. Then I add my 5, so plus 9 plus 5. And sure enough, I have what I started with. Okay, I have what I started with. So that's how you verify that you completed the square properly. Please note, when you get comfortable, you can just automatically borrow the 9, or the minus 9 plus 9, from the 14 if you want to. But what I've done is first learning these steps. These steps I've shown will help on the more complicated ones. Let's get to a more complicated one. All right, what if the coefficient in front of the x squared, and this should be x squared, has a 5? Well, that's no good. You can't complete a square easily with a 5 in there. There are some completion of the squares that have a 5, but it doesn't usually work with the number that you are presented with. So you have a choice. You can keep the 21 in there. So I got minus 21. But I find it, at first, it's easier to move the minus 21 out of there. So yes, you could keep this minus 21 in there when you factor out the 5. And that works as well. That helps you keep the numbers separate. Now, I should actually go and show you that method as well. But what I do is I just move the minus 21 aside, and I focus on my perfect square here. Well, I can't have a 5 in front of the x squared, so I'm going to factor out a 5, and I get x squared plus 4x. And here we can follow the same steps. I have to ask myself, what perfect square without the number will create x squared plus 4x? And simply, to find it figured out, you divide the 4 by 2. So that means it's x plus 2. When I expand x plus 2 squared, sure enough, I get what I want. X squared plus 4x. But I also create a number I don't want, plus 4, which means if I want just this part, I have to take this, which brings out about this whole thing, and subtract a 4 so that I get rid of this plus 4. So sure enough, if I take x plus 2, and I got the 2 simply by dividing this 4 by 2 squared, and I subtract a 4, will I get what I want? Will I get just this portion of it right here? Let's see. So if I expand this, sure enough, I get x squared plus 2 plus 4x plus 4, and then I have to subtract this 4 here, which sure enough, it gets rid of that number. And what am I left with? Exactly what I want. This is my goal, exactly what I want. So that's why we're subtracting a number constantly, to get rid of this unwanted number that's produced by this expansion. So I only want the first 2 terms of the perfect square. So you're always subtracting the number you don't want. Okay, what will create that 4x? Well, divide it by 2. You get 2x. The x is already going in the front, so we can just divide that by 2x again if you want. So it's 2. But the shortcut is just take this number, divide it by 2. Okay, I'm looking for always just divide the number by 2. So I get this. I can create this in the middle like this, but obviously I'm going to create that unwanted number that I'm just discussed. However, when I expand that, I will create an unwanted plus 4, which is plus 2 squared, and I only want this portion of it. So I must subtract 4. So this is what you want to aim for, and this part of it gets rid of that unwanted 4. The problem is this 5 is still multiplying everything in this bracket, and you want that. But this minus 4, you'd have to leave it in a bracket like that, which is not what vertex format looks like. Vertex format would look more like this. It doesn't have an extra stuff going on inside the bracket here. Okay, so the question is, how do I get that minus 4, which is being multiplied by this 5, out of this bracket? It's quite simply, I multiply the 5 times the minus 4 to get it out of the bracket. Okay, so I need to get that minus 4 outside with the minus 25, but technically it is just being multiplied by the 5. So to get it out of the bracket, I simply multiply it by the factored out coefficient, the 5. When I do, 5 times minus 4 creates that minus 20. Now that it's out of the bracket, these numbers can be added. It cannot be added until I apply this 5, which is multiplying everything in this bracket, to just the number. I can now get rid of those extra brackets. I don't need these things here anymore, and I'm left with 5 times x plus 2 squared minus 41. This, if I expand it, should achieve what I started with. That's the goal. But notice, I now have it in vertex format. I now have it in vertex format. To prove this works, I then expand it to see if I get that. So sure enough, it's 5 times all of this, minus 41. 5 times all of this gets 5x squared plus 20x plus 20, so I get that. Then when I subtract the 41, I get minus 20. I get this, which is exactly what I wanted. So I've successfully converted this standard format into a vertex format, and I can immediately see the vertex of this thing is minus 2 comma minus 41, which is the point. I'm trying to figure out the vertex. Now there's actually a shorter cut to figure out the vertex. I believe it is, you can figure out the x value of the vertex by taking the 20, taking the b value here, making it negative, and dividing it by 2a. What's the a value? It's this here. And that will work as well. So minus 20 divided by 2a, which is 10, which it becomes minus 2. And sure enough, that got me in the x value, and then you can just plug the minus 2 into the formula to figure out the y value. That's also a faster method. So just be aware that you should also learn that minus b over 2a of the standard format will tell you the x value of the vertex, which can then be plugged into the formula to give you the y value of the vertex. That's a valid technique. But right now, we're learning completing the square. Let's go back and do the thing I haven't done in all this video and include the minus 21 in the bracket and see if we get the same thing. So what I'm saying now is I'm going to factor out a 5. I'm going to factor out a 5 out of all of this. I'm not going to separate the 21. And we're going to see if we get the same thing. You're going to find it a little bit more cumbersome because you end up working with fractions. So if I factor 5 out of all of this, that saves me the time of not having to use the 5 later on. Okay, I get x squared. That's easy enough. I get plus 4x. That's easy enough. And suddenly I get this weird thing, minus 21 over 5. Now I can leave it like that, or I can convert it to numbers. That happens to be minus 4 and 1/5. We can convert it back and forth as we need to. Now I can see that I have to complete the square here normally. So I get x plus 2 squared, and I have to get rid of that unwanted 4 still. And then I have this minus 4 1/5. So you can see that it gets pretty complicated. And it's all being multiplied by 5. Now it still works, but I must add my like terms. 5, x, all in a big bracket. Keep in mind it's all in a big bracket. X plus 2 squared. What's minus 4 1/5? It's minus 8 and 1/5. Okay. And finally, when I keep in mind all that's in one bracket, when I get rid of that, I have to multiply the 5 to get it out of the bracket. So I get 5 x plus 2, and here's the tricky part. What is 5 times minus 8? It's minus 40. What's 5 times 1/5? It's 5 over 5. So that means that adds an extra 1 to my 140. Or you can convert this all to fraction. So that would be 41 over 5. And when I multiply that by 5, the 5's cancel out, and I'm left with minus 41. So it works that way, but I'm going to let you know that this part of it can get hellish when it gets really complicated. You'd be better off learning this method, but also partially completing the square that we're going to get to. But there's even tougher ones. So let's get to a tougher one. This one is hard, going to be hard because the middle term gets pretty complicated. Let's look at it. I know from my theory that I'm going to put the minus 4 aside. So I'm looking on 5x squared plus 2x. But the problem is I don't want that 5 in there. So I'm going to factor 5 out of both of these terms. So if I factor 5 out of both of these terms, I get the very uncomfortable this. This makes it hard. So first, put the minus 4 aside. Boom, done. Next, factor out a 5. I get a very uncomfortable plus 2/5 x. Well, that's okay, because we know the formula is to complete the square, all we do is divide that number by 2. So to divide 2/5 by 2, you have to remember your rule of fractions. Take 2/5 and multiply it by the reciprocal of the bottom fraction, and you get 2/10. So that means a half of 2/5 is 2/10, which makes sense when you think about it. To verify, you can just multiply by 2, and sure enough, you get back to 2/5. But 2/10 is a half of 2/5, which in your head you're going to have to get used to. Just notice a pattern that the denominator increased by double. So let's see if that's true. Is a half of 1/5 1/10? Let's multiply by 2 and see. Yeah, 2 over 10. Simplify 1/5. So it looks like to half a fraction, all I have to do is double the bottom. And you will discover that's true. So for instance, what's half of 2/7? It is 2/14. So it's not too hard. You just got to get used to the notion that we're actually multiplying it by half to get it to there. So always half this number. Now I show you the complicated fraction technique, but now we know a shortcut. This is what my square would look like. 5 x plus 1/5 squared, but I'm also going to create an unwanted number. The unwanted number that is created is always the square of this part of it. So 1/5 times a fifth would create an unwanted number of 1/25. That's where these get hard, right? That's where these get hard. Let's see. Okay, yeah, I'll go back to that. That's where these get hard, is figuring out the unwanted number. The unwanted number is 1/5 squared, 1/25. So that means when I expand this, I get an unwanted plus 1/25. So that means I have to subtract it so that this portion here expands and creates this portion here. That's why we do it. Okay, but now I need to get that minus 1/25 out of the bracket, so I have to multiply it by 5. I get minus 5, 1, when I do that, 5 times minus 1 over 25 is minus 5 over 25, which simplifies to 1/5. So to get it out of the bracket, it becomes this. Now, look at that. I have exactly what I want. I have my nice 5x plus 1. All I have to do is adjust this. And minus 4 minus 1/5 is that, or as a fraction, it's that. So that means the vertex of this thing that we started with is minus 1/5, because you always make the opposite here, comma, minus 21 over 5. To make sure, just put this original one into Desmos and go look at the vertex, and you will indeed discover that the vertex is minus 1/5, comma, minus 21 over 5, which is also minus 4 1/5, which is also minus 4.2. So you'll see that on Desmos. And instead of minus a fifth, you'll see minus 0.2, because Desmos doesn't work in, well, you can make Desmos work in fractions, but it's going to show it to you in decimals. Sure enough, if you want to prove it, you just expand it. So here's the expansion of what I have in the middle here. That's the expansion of that. When I multiply by 5, this is what I get. And don't forget, that's the number we put aside, right? Oh, sorry, that's that number right here. So we've got that number right there. And then when I add this number to that number, I sure enough get that. And this part simplifies to minus 4. And that's exactly what we started with. So if you want to see if you got the right completion of the square, if you're doing it right, or if you're learning it right, whatever you ended up with here, okay? Whatever you ended up with here or here, if you expand it, you should get what you started with. That's how you know if you completed the square properly. Now on the right side, and I can probably attach all these too, but on the right side, this works too. But I wouldn't bother with it. All they do here is they put the 4 on the other side of the equal sign, just so that you can focus on completion of the square. And then you bring the 4 back. But it's really the same technique. You'll see that in YouTube a bit. I personally find it makes it a little bit more confusing. So all they're doing here is that instead of putting the minus 4 just to the right as I do, they actually put it on the other side of the equal side as plus 4. Then they focus on their completion of the square. And then they bring the minus 4 back to that side as the plus 4 back as a minus 4. I actually think it's silly. Now, let's go to a far more useful technique of partially completing the square. I actually prefer this. All right, my favorite technique is partially completing the square, because you save so much time. Let's use the same example we just did. Let's put the minus 4 aside, and we're going to factor out the 5, and we get this tough little thing here that we had to divide by 2, which we learned is 2 over 10, simply doubling the bottom denominator, which is 1 over 5. So that means the half of 2 over 5, which is hard to see, is 1 over 5, which makes sense, though. When I multiply that by 2, it's 2 over 5. So that means 1/5 is indeed the half, right? So I can do it the long fraction way. So this is where my square would be, and I'm worried about that extra number, but stop, because you'll find that figuring out that extra number is the pain in the butt part, right? We now know, though, however, from this alone, I know my x value of my vertex is that. Well, that's great. We now know the x value for the vertex is minus 1/5, which is the opposite always of what's in here. We don't need to do anything more. Let's just put minus 1/5 into the original equation, and it will spit out the value we want. Okay. So here's the original equation. I'm going to put minus 1/5 everywhere I see an x. Now remember, x alone is squared. You'll see in a textbook they always skip the brackets, and they shouldn't, because really this bracket should go all around this part of it, because I'll see students who they'll square the 5 as well. And that's not what this is saying. This is saying just the x is squared. So minus 5th squared becomes 1/25. X here, 2 times minus 5th becomes minus 2/5. 5 times this 1/5 becomes 5 over 25, which becomes 1 over 5. And then I simply add these things. Plus 1/5 minus 2/5 minus 4 is minus 4 1/5. That is the y value of our vertex, so I can just plug it in here now. I actually love completing the square. So completing the square is, once you figure out this part of it, you now know the x value for your vertex, and all you have to do is plug it into the equation, or let your calculator plug it into the equation to get the result. This result is always going to be the y value of your vertex, which is always here in the vertex equation. So that means partially completing the square works really well. Bingo. I love partially completing the square. I encourage you to learn it. You can also learn that technique, which said that we're going to take minus b over 2 times a, which is 10. Okay, so 2 times a, I'll write it like this. Minus b is minus 2. 2 times b is 10. We now have our x value for our vertex, right? Which happens to be the opposite of this, right? But this is the exact x value. We now can plug that in all the way to here. So if your teacher lets you use the minus b over 2a method to get to the x value right away, you can even speed up partially completing even faster. However, I believe learning completing the square is a valuable tool, and this is why. All throughout math is about having an existing expression and breaking it down into components that make it easier to understand. And you're allowed to follow the rules of math no matter what. People have a big trouble subtracting negative numbers. Well, I can break that 20 down into minus 7 and minus 13. That's still minus 20. It's quite clear that these cancel out, and I'm left with x minus 13. This sometimes was easier to figure out than trying to figure out what's plus 7 minus 20. Now, I know for lots of you that's not an issue, but obviously I'm talking about crazy complex situations. And obviously I'm talking about crazy complex situations. And you're going to have situations where you want to manipulate things even more. I'm going to break this down on the next line. I'm going to leave this for now. I'm left with what's left if I take that and that away from that. I'm left with minus 8,031. Great. That means these will eliminate, and I'm just left with this. All right. I've broken 36 down into that. I've broken 8,000 down into that. Some of you won't even have to do this. So clearly these cancel. And I'm left with plus 5 minus 8,000, which is clearly minus 7,995. Now I did that quickly. I might have made an arithmetic error. But the point I'm trying to make is, so I'm left with x minus 7,995. The point I'm trying to make is, you can break down math so long as you follow the rules of math over and over again. A very good example is letting u stand for something complicated, like when you see in a cosine, when you see something like figuring out cosine of 2 pi x minus 9, you can let u stand for 2 pi x minus 9 and simply solve for cosine u. Once you figure out u, you then put it over here and solve this part of it. Math, complex math especially, is all about finding interesting methods to using the rules of math to making life easier. And all of math is about finding better techniques to do what was done in the past.